this is, so put people in a line and choose the each choice is counted k factorial times n minus k factorial times. These two are very simple examples, but somehow you will see that ideas like that can be used in much more complicated settings, so, which will appear later in this lecture. Also, maybe I would like to say that this number, n choose k, appears very naturally in algebra. So when you take the a plus b to the power n and try to open the brackets, try to fully expand it, you get these numbers as coefficients of individual monomials. The coefficient of a to the power k, b to the power n minus k is equal to n choose k. So, for example, there are these formulas that we all have seen and used many times. So I will be talking about counting in a slightly more complicated context. So roughly speaking, when we talk about trees in mathematics are a particular type of graphs. And graph, again, for purposes of combinatorics, is about counting the ways of connecting several points in various possible kinds. And this result that I am going to discuss was actually discovered many years ago, more than 100 years ago, in 1889 by a remarkable mathematician of those times, Arthur Cayley. And somehow some of his motivation was from combinatorics, but also his motivation was partly coming from algebra, and the proof of this result that I'm going to explain actually uses some intuition coming from complex analysis, so it is kind of a nice blend of different kinds of mathematics. So let me first give you some little reminder for terminology that I am using. So when I'm talking about graphs, I am talking about that we have several vertices, and we have a rule which tells you which vertices are directly connected. So you have something like this. You have several vertices, and some of these vertices are connected. And I want to emphasize that we only care about knowing which vertices are connected. It doesn't really matter how we draw the corresponding thing on the plane. Because, for example, I could draw this with vertices 1, let me call these vertices 1, 2, 3, and 4. Or I can do something like this. And these two are, for me, I do not distinguish between those two pictures, because the only thing that I care about is that I look at these vertices, and vertices number 1, 2, and 3 are pairwise connected, and the vertex number 4 is only connected to the vertex number 3. So the way you draw it is absolutely irrelevant. These two pictures are considered exactly the same. So in principle, graphs appear in mathematics a lot because they also appear in real life a lot, because graphs is just give you a convenient way to represent relationships between different objects. So for example, you can take the graph whose vertices are capitals of Mexican states and then draw a line between the two capitals if there is a direct flight between the two of them. And of course, this graph will be kind of special because there will be Mexico City, which sort of is connected to everything, and most other vertices are not connected to each other, because to fly from one place to another you usually go via Mexico City. So that would be kind of a very specific type of graph. Now, what I call a tree is a graph without loops or cycles. So this means that these pictures are not allowed because there is a cycle. I can go 1, 2, 3 and go around. But for example, something like this, 1, 2, 3, and 4, is perfectly fine. So essentially, you should think that a tree is a graph where between any two vertices there is really unique way to go from one to another. And, well, those are called trees because, well, you know, a picture like that kind of slightly resembles, well, child's drawing of a tree, let's say. And also it would be important to talk about combinatorial objects that usually are called rooted trees. And a rooted tree is a tree where one of the vertices is marked and distinguished from the other. So for example, let me show you. So if we only care, suppose we have only two vertices, then there is just one tree. We connect these two vertices by an edge, and there is nothing else that we can do. But if we're talking about rooted trees, there are two different rooted trees, because we can say that the root is at the vertex number 1 or at the vertex number 2. And so we may, when we decide which vertex is the root, we make a choice. And so there are a bit more different things that we can do. So this leads me to a simple remark. So if you have n vertices, then the number of rooted trees on these vertices is n times the number of trees, because you can basically choose any of the vertices to be a root. So this is a very silly, simple remark, but it will be useful for us at a later stage. What Cayley noticed in late 1800s is that the number of trees with n vertices, actually, if you start computing, there is a very nice pattern. So let me see. So there is one tree with just one vertex. That is very obvious, right? So, okay, so let me erase all this. So you can only, if you have one vertex, then there are no edges. There is absolutely nothing, no degrees of freedom, so to say. Then there is, if we don't care about the root, there is just one tree on two vertices, as I explained. What about three vertices? That is also very easy. So if we have three vertices, then we can only have something. So let me actually draw you all the three trees with three vertices. And here I suppose I would like to emphasize that in principle I could also draw something like this, but this tree is exactly, these two trees are exactly the same, because in both trees the vertex number 1 is connected to the vertex number 2, and the vertex number 3 is connected to the vertex number 2, and no other connections are there. So from our, as I said, it doesn't really matter how we draw trees on the plane, so these two are exactly the same. So there are three here, one here, one here. So I will not draw you the 16 trees on 4 vertices, because it will just take quite a bit of time, and I certainly will not draw you 125 trees on 5 vertices. But already with these numbers, you can see, in fact, you can guess some sort of pattern, because 16 is 4 squared, 125 is 5 cubed, and so in fact, one natural guess is that the number of trees on n vertices is equal to n to the power n minus 2. And so this, in fact, is correct, and this I'm going to explain to you today why this is correct. And of course, we discussed already that number of trees is nicely related to the number of rooted trees. So for the number of rooted trees, you have, the numbers are 1, 1, 2, 9, 64, 625. So in fact, of course, the pattern is that the number of rooted trees is n to the power n minus 1. And in fact, well, I'm going to prove this result. It will be a little bit easier to nicely present the proof for the counting of rooted trees. But as you know, the number of trees is the number of rooted trees divided by n. So these two results are absolutely equivalent. It's enough to prove one of them. Okay. Yes, so there are many different proofs. So I chose to present to you a proof which uses some intuition coming from analysis, just to show you how different areas of mathematics can be connected to each other. But there are, in fact, there is somewhat, I wouldn't say direct, but combinatorial proofs which only use arguments like arguments of counting that don't use any machinery which is external to combinatorics. So first of all, let me outline the strategy. The strategy is a three-step strategy. So first of all, it is possible to express the number Rn of rooted trees on n vertices in terms of the numbers of rooted trees with less than n vertices. And that will be the first argument, which it will be some expression. It won't be simple. It won't imply anything directly, which is not too surprising because, you know, the number of rooted trees on n vertices is equal to, we expect that it's equal to n to the power n minus 1. The number of rooted trees, for example, on n minus 1 vertices is equal to n minus 1 to the power n minus 2. These two numbers are not very cleanly related. It's not like one is a nice multiple of the other and so on, so you shouldn't expect a very easy formula, but there is some formula. Then these all, so there will be some recurrence relation, so some formula for every n. And then what I will do, I will assemble all those equations in one equation, but not involving numbers, but rather involving power series. And that's when we move from algebra to analysis. And then I'm going to use some simple facts from complex analysis to study that one equation. So that's the plan. Now let me tell you more specifically how these how this proof goes. So first of all, let me explain to you how to obtain some sort of recurrence relation on these numbers. And the idea is that rooted trees, by design, have some very nice recursive structure, or fractal structure, because if you take a rooted tree, if you have a rooted tree, so it has some root. It has a root, and then to that root you have this root has several edges connecting it to other vertices, and then everything, the part of the tree which each of the parts that you obtain if you just delete those edges, each of these parts itself looks like a rooted tree, but with a smaller number of vertices. So somehow, to get a rooted tree on many vertices, you take many smaller rooted trees and connect them to the root. And this simple observation leads to some recurrence relation. Yes, so this is exactly what I said. So now, let me say, let me put it like that. So suppose to have the root of our tree is a vertex number k, and then there are many trees attached, rooted trees attached to this vertex, and Somehow the easiest way, the cleanest way to count is to use the following notation, that suppose that there are among those trees attached to the root k are n1 trees, each of which has one vertex, m2 trees with two vertices, and p trees with p vertices. So somehow, why am I doing something like that? Because later we'll, okay, let me maybe give you some little hint. So somehow suppose that, so we have a tree with a root, the vertex number 2, then I can consider these two trees, and these trees are, of course, exactly the same. We don't find any difference between them because both of them have 2 as a root, and vertices 1 and 3 are both connected to the root. It doesn't really matter that in the plane those trees look a bit different. So somehow, if you have 2 trees attached to the root which have the same number of vertices, then there will be some in most obvious way to count, there will be some double counting that we need to take care of. And that's why I group these trees into groups with the same number of vertices. So that's a very important thing to keep track of. And it's important to remember that these numbers are not quite arbitrary. We still have the total number of vertices equal to n. So we have the root, and we have all these vertices of the trees attached to the root. So we have m1 trees with 1 vertex each, m2 trees with 2 vertices, and so on, mp trees with p vertices. So m1 plus 2m2 and so on plus pmp is equal to n minus 1, to the number of vertices except for the root. So suppose that we fix the number p, so fix the biggest number of vertices in the trees attached to the root, and we fix these numbers m1 and p. So we know exactly that we have m1 trees with 1 vertex, 2 trees with 2 vertices, and so on. Suppose for the moment we fix them, then we will need to add all things by all possible choices. But let's make this one particular choice. Then I claim that the number of choices to build a rooted tree with this kind of data is given by a relatively easy formula. So let me explain what this formula means. So first of all, I have this factor n in the beginning. This number n is the number of ways to choose the root. Because there are n vertices, we need to decide that one of them is the root. Then we take the number n minus 1, and I want to split the remaining n minus 1 vertices into groups which will be vertices of the same rooted tree. And since we have n1 trees with 1 vertex, m2 trees with 2 vertices, and so on, and p trees with p vertices, the number of ways to do so is given by this fraction, n minus 1 factorial, and then divided by the product by m1 times 1 factorial, m2 times 2 factorial, and p times p factorial. This is very similar to what we were doing when we were choosing k people out of n, right? So you put those n minus 1 vertices in a line, and then as you take the first vertex as one of those m1, the second, and so on, then you take pairs to, and the order doesn't matter, so you have to divide by all those factorials. So this is exactly the same counting. What else is here? There is this fraction 1 over m1 factorial, m2 factorial, mp factorial. This is related to the double counting that I mentioned before, because this way you will distinguish between different choices for example, that counting will make these trees different, because this one, so we can choose the first group of consists of 1, the second group consists of 3, or the first group consists of 3, the second group consists of 1. So we need to divide by 2, and more generally, we need to divide by m1 factorial if there are m1 one-vertex trees attached to the root. And of course, we will need also to take the product of the number of rooted trees on one vertex m1 times the number of trees of 2 vertices m2 times, and so on. And that's because once we make all those choices, we really need to identify which combinatorial structure that each of those rooted trees have. So this is maybe the most obvious part of the formula. All that little counting on the left, this is, you need to think a little bit about it, but somehow this product on the right certainly is there because you need to choose which of the rooted trees you put at each place. Okay, so this, yes, I mean, believe me, so this is the most, well, the scariest formula of this lecture. Everything else will be much easier. So first of all, this formula that I just copied from the previous slide can be, of course, simplified substantially like this. So first of all, I can multiply n by n minus 1 factorial, and I get n factorial. Then, so this, the product of m1 copies of r1 is, of course, r1 to the power m1, and here you have the product of m1 copies of 1 factorial, so you have this. Same with r2 and 2 oh my god, okay, so forget about these factorial signs. So there are absolutely no factorial signs there. So it is r1 over 1 factorial to the power m1 over m1 factorial 1 over m2 factorial r2 over 2 factorial to the power m2, and so on. Yes, well, you know, when you start typing a long formula like that, where you have factorials almost everywhere, you are, I suppose, tempted to put them everywhere, and it goes completely wrong. But yeah, right. So now, okay, this persists. So in any case, to get the number Rn, as I said before, we need to add these things over all possible choices of these P, M1, MP, subject to these constraints. That is not very pleasant, but I'm not going to actually add it. I'm going to explain to you how to package this recurrence relation into something a little bit better. Oh yes, now it's better. So so somehow we have here something which uses not quite the number rk, but rather rk over k factorial. I want to emphasize that, yes, so you add all these numbers together and you say that this is equal to rn. And in fact, this means that you can divide everything by n factorial and say that rn over n factorial is equal to something a little bit more simple. So it makes sense to focus on the coefficients rn over n factorial. And this, maybe I should mention that it's a very important general phenomenon that somehow n factorial here counts the symmetries of the set of vertices, because you can, if you have n vertices, you can rename them in n factorial ways. And this is a very usual combinatorial situation, that when you are counting something, usually formulas get better if you divide by the number of symmetries. So this is a very general phenomenon. And so the algebraic trick I'm going to use is the following. Let's assemble these numbers in a power series. So let's take some variable that I call z, and let's consider the power series r1 times z plus r2 z squared over 2 factorial plus, so the coefficient of z to the power n is that number rn over n factorial. So that's the new protagonist in the story, and using this power series, it turns out it's very easy to write a very nice equation that we can then deal with. So yes, let me, so I copy that series again, and so this is the equation. So I claim that our recurrence relation just means that this power series R of Z is equal to Z times the exponential of R of Z. And exponential, it's understood in its usual way, so where you know, the e to the power x is given by the Taylor series that we all have seen many times, just the sum over xn over n factorial. So I take this formula, and instead of x, I substitute r of z. So somehow, so this is not entirely obvious, but it's quite easy to see if you start actually. If you start figuring out what these formulas mean. So if you substitute R of Z given by this into everywhere here and start multiplying. So for example, when you have R of Z squared, this means that you will have the coefficient of Z to the power n here will be equal to the sum of things Ri times Rj times some numeric coefficient that is expressed via factorials and so on. So somehow this equation says that if you take the coefficient of Z to the power n here on the left, and the coefficient of Z to the power n on the left is just Rn over n factorial, then it is equal to some big sum of products in n times factorials. So it's not entirely surprising that the recurrence relation that I told you about is packaged like this, but you need to actually do some work to convince yourself that this our recurrence relation translates into that. I am not going to do it right now. For this particular statement, I suggest that you believe me, and then later when you come home, you can actually you can try to see what happens when you multiply out all the brackets and open them, and you will see that it will be exactly the recurrence relation I had on the previous slide. I mean, it is one of those things where if you try to carefully explain it, everything gets even more confusing, but if you try to do it yourself and see what is going on, you will easily convince yourself that this formula is correct. So that's exactly what I said. The upshot of what I explained so far is that the Rn over n factorial is the coefficient of Z to the power n in this power series, and this power series satisfies this very simple equation. And now we are going to use some little fact from complex analysis, namely it is called the Cauchy residue formula, and it states the following. So suppose that you have a power series of this form, and strictly speaking, of course, it's you would require that this power series actually converges in some neighborhood of zero, but that's a little silly little technicality that let us ignore for a second. Let us then the Cauchy residue formula says that the nth coefficient of this power series is given by this contour integral. So you take some little contour around zero, and you integrate the function a of z divided by z over n plus 1 over this contour. So you take 0 on the complex plane, you take some contour. So for example, you can take the circle, the absolute value of z is equal to some number epsilon, and you integrate around this contour, and then you divide by 2 pi I. So that's it is one of the first statements that are normally proved in a complex analysis course. So I assume that if you studied complex analysis, you know this formula, and if not, then when you study complex analysis, that will be one of the first things that you will learn. So somehow the way to remember this formula is to say that when you integrate something over a contour around 0, then the only thing which matters is the coefficient of 1 over z, which is called the residue. And everything else integrates to 0. So that's why we had this power series. We divided by z to the power n plus 1. So then the coefficient of z to the power n in this series, after you divide by z to the power n plus 1, becomes the coefficient of 1 over z. And so that's the essence of this formula. So we conclude that n over n factorial is just given by this integral. And so far, you can say that what's the point? So we moved from a very simple elementary combinatorial question to some bizarre question about computing an integral. And so what's the benefit of that? And the benefit is that when we compute integrals, we can change variables of integration. And it turns out that it is possible to change the variable of integration in a way that you can almost immediately compute this integral. So let me show you how this is done. So let's just take new variable y equal to r of z. So this r of z is this unpleasant thing that we want to get rid of. So let's denote it by something new and try to get rid of it completely. Okay, so we have our functional equation r of z equal to z times e to the power r of z. So in other way, this means that, so since r of z is equal to z e to the power r of z, this means that z is equal to r of z e to the minus r of z. So we can multiply both sides by e to the minus r of z. So this means that we recall that r of z now is this new variable y, so z is equal to y e to the power minus y. Very good, we got rid of r of z here, but we also need to change change variables in dz. So there is the formula for change of variables in integrals says that. So it's very easy to remember if you interpret this expression in a meaningful way. So dz is equal to dz over dy, where dz over dy is the derivative of z with respect to y, right? So, but we already know that z is equal to y e to the power minus y. It's very easy to differentiate that with respect to y, right? So the differential of the product, the differential of this with respect to y, we differentiate y, we get e to minus y. We differentiate e to minus y, we get minus y e to the power minus y. So this is straightforward. So z is equal to y e to the power minus y, and dz over dy is equal, we see 1 minus y e to the power minus y. So we can just substitute everything inside this integral. So r of z is y, z is y e to the power minus y, and we raise it to the power n plus 1, and dz over dy is this y minus y e to the power minus y. So we got rid of r of z completely, right? So we really have a very elementary integral that only has y and exponential. There is nothing mysterious left. And this, let me simplify a little bit. So just by doing algebraic manipulations, it's very easy that we get to see that we get this, right? Because you have y to the power n plus 1 in the denominator and y in the numerator, so you get y to the power n in the denominator. You get e to the power minus y to the power n plus 1, and e to the power minus y here, so a little bit cancels, you get e to the power ny, and 1 minus y remains. So this is just elementary algebraic manipulation. And this, finally, let me write like this. So let me separate 1 and y. So it's the integral of e to the power ny over y to the n minus e to the power ny over y to the power n minus 1. And here we can, of course, apply Cauchy residue formula, because we remember that when we divide by y to the power n, this means that it is the coefficient of y to the power n minus 1 in this power series e to the power ny. And when we divide by y to the power n minus 1, this means that we look at the coefficient of y to the power n minus 2 at of e to the power ny. So this is what I said here. So, but e to the power ny, we know what power series that is. So the coefficient of y to the power n minus 1 here is n to the power n minus 1 over n minus 1 factorial, and the coefficient of y to the power n minus 2 in this series is n to the power n minus 2 over n minus 2 factorial. Now you take this to bring it to the common denominator, do simple algebraic manipulation. So the answer for our integral is n to the power n minus 2 over n minus 1 factorial. And we recall that this integral that we started with computes r to the power rn divided by n factorial. So rn over n factorial is equal to n to the power n minus 2 over n minus 1 factorial. So rn is equal to n to the power n minus 1. Exactly what I promised. So that is this proves the formula for the number of rooted trees, and by the argument we had before, we can conclude that the formula for the number of trees without designated root is n to the power n minus 2. So somehow the main part of the lecture finishes here, and you see what I like about this proof very much is that it really brings different parts of mathematics together. You start from a question which is an elementary combinatorial question, which in principle, at least in proving that something is equal, some counting thing is equal to n to the power n minus 1, it's something that you could have in principle encounter, I don't know, in a mathematical Olympiad or something like that. But in particular, among many other strategies to prove that, you can actually use some intuition coming from analysis. And this really, I think, teaches us a very important lesson that different parts of mathematics are very much interconnected, and sometimes interconnected in very unexpected ways. So somehow, if you decide that you want to study combinatorics, it doesn't mean that you don't need to put effort in learning analysis or in learning algebra, because sometimes this can help you in an unexpected way. I want to conclude with a very short remark. So for me, one of the reasons I recently got interested again in thinking about these numbers is that they actually appeared in a completely different story that is related to one of my current research projects. So I was studying a certain algebraic structure, what is called F-manifold. So I mean, now I'm going to just show you two slides that bring us a little bit closer to very recent research mathematics. So all the previous slides, I was hoping that at least to some extent what I was explaining should be comprehensible. For these last two slides, if you don't understand what's going on, it's not a problem at all. So this is the definition. So an F-manifold, in particular, it gives rise to a vector space where you have two operations. You have an operation that I denote by circle and an operation I denote by this cross, where circle is a commutative operation, so it's like the product of numbers. Cross is an anti-commutative operation, like the vector product in 3 dimensions. And the circle operation is associative. The cross operation satisfies this more obscure identity, and they are related by this even more bizarre identity that at this stage certainly shouldn't mean anything specific to you, but it's just that it's some sort of algebraic structure, and understanding things about this algebraic structure is important for purposes of geometry and mathematical physics, it so happens. So this is the result that I recently was able to prove. So let's consider all possible operations with n arguments that you can build out of these binary operations. So you take these operations and start substituting them into another, forming operations with more arguments. Then these operations that you can form, well, they form a vector space, and the dimension of this vector space turns out is n to the power n minus 1, and somehow this space is related to the space whose elements are all possible formal combinations of rooted trees with n vertices. So there is this kind of mysterious result. And to clarify what exactly I mean, I can say that for n equal to 3, you have these 9 operations that form a basis of that vector space of dimension 3 squared. So, for example, the circle operation is associative, so we can, and commutative, so we can form only one product, only one operation with 3 arguments out of it. And with other things, you have to be a bit more careful. So that's, and somehow this result is another illustration of what I was saying. So you might start with some question which doesn't have any even superficial relationship to combinatorics, to rooted trees, to anything at all, but nevertheless, once you start working with it, you realize that there are some unexpected relationships. So the more mathematics you learn, which is not directly related to what you're going to study, the better, because this will give you an advantage of noticing unexpected connections. That's basically the main message of this lecture, and I'll stop here.
How did you use the theorem of counting trees to apply it to the theorem you proved?
Yes. In the beginning, I told you that one of the motivation of Cayley was coming from algebra. So Cayley was studying an algebraic structure that formally encodes what happens when you compute higher order derivatives of functions. And that algebraic structure now has been, it's an algebraic structure which now people call the structure of a pre-Lie algebra, which has been studied very systematically for many years. And that structure is related to combinatorics of rooted trees in a very direct way. What happens in my story is that it turns out that you can take this structure of a pre-Lie algebra and consider in some way a degeneration of that structure. And for some miraculous reason, a degeneration produces this structure of an F-manifold. So it's an idea. To make this idea precise and to convert it into a rigorous proof, you have to do a lot of hard work, but somehow, because from the algebraic point of view, these two algebraic structures, they actually they look very different. The structure of a Aprile algebra is amenable for studying by many standard methods. This structure of an F-manifold doesn't really fit directly in any standard theory.
¿Alguna otra pregunta? No, si no hay más preguntas, volvemos a agradecer a Vladimir por su plática.
Gracias.